the theory of everything. And there's two parts to that. There's a physical part, which I think pertains to physics. And there's the mathematical part, which is, an equation they've been looking for. And so the TOE really involves a little of both. We're going to deal with the physical part first. Okay, I'm going to talk about the physics part first. And in the second half, we'll be talking about the mathematics, how the mathematics relates to that physical part that I explained earlier, right? Okay, so let's start with the physical part, okay? Is there a way to unify, especially light with gravity, electromagnetism and gravity? Is there a way to unify, have a single theory, a single mechanism? And it's really two mechanisms out of the same entity, the same mediator. That's what it's all about, okay? And so let's start there. Let's start with what we had, and we have something like this even to these days, right? Let's see if I can put it up here. And as we have these gentlemen, okay, and they were only a few that I selected, probably the most important ones that you see up there. And what they proposed, what they came up with, was a mathematical concept, the electromagnetic wave that is still being used even to this day, okay? And what's wrong with this? Well, this is what I can say is what's wrong with it. It's a concept. It talks about two fields, and the two fields are made of vectors. Those arrows there that you see, those are vectors. And as you can see, those are all concepts. And one of the first lessons you have to learn in physics is that you need objects. You can't do physics without objects. And that's a hard lesson for people to learn. They want to do it with concepts such as field and vectors. And no, if you're going to give a physical interpretation, you're going to do the physical part of your presentation, of your dissertation, you need a physical object, okay? I mean, you can take the elephant, right? And say, look, what's the mass of the elephant? Well, it's so many tons, 5 tons, whatever, right? And you condense it into a single point. You say, well, I took the elephant and I condensed it into a little point because we're not interested in the elephant for mathematical purposes. We're interested in the mass. That's what we're going to be putting in an equation, right? The mass of the elephant. No problem. No problem whatsoever. But if you're going to move something, you're not going to move the point. You got to put the elephant back in there. You got to move the elephant. You can't move the point. Okay, and that's where people get confused because they start moving points and treating the points like physical objects when what you have is a mathematical concept, which is the center of mass. And this is more or less what's happened here with a wave. They take in a wave, the electromagnetic wave, and they start shaking it, moving it, doing things with it. You can't do that. You got to put a physical object there. And people don't understand that. So what we've done is we replaced the wave, right? And we replaced it with the, in a second here, we replace it with a rope, right? In this channel, this is what we propose. We're saying that the electromagnetic wave that these people proposed was really a rope, a pair of twine threads, a DNA-like object, right? And they confused it for a electromagnetic wave because, yeah, there is a waviness to it. First of all, a structural waviness to a rope. And then there's this torsion. Not a transverse wave, not a longitudinal wave. It's a torsion wave. In other words, the thing twirls in situ and you have all these goosebumps moving along, the rope. And so that's what we're saying, that the mediator of light and of gravity is that rope. Now, as far as light is concerned, I think we have some credit to our name here, okay? And that's because of this. We can explain the constancy of the velocity of light, okay, the speed of light. And you can see there that you have that little equation, little c, velocity of light, speed of light, right, equal to frequency times wavelength, okay? And the only thing imaginable that can represent that equation is a rope. There is no other structure. Okay? There is no other structure. I challenge anyone in the universe. I'll challenge even God to come up with a thing that can imitate that can simulate that equation. And I'm telling you, there ain't. Okay, there's no such other object out there. It's got to be a rope. Okay, this is it, folks. It's a rope. Okay, so you can see it has all the features of the so-called electromagnetic wave, which has been corroborated, over 100 years. It's got wavelength. We call it the link. It's the length of a link. It's got amplitude, right? The height, okay? And it's got frequency, because you have all these goosebumps. And the number of bumps there is the frequency. If you untorque a rope, right? Let's untorque it. The links are longer, and you have fewer links. And if you torque it more, you get more links, more frequency, and each link is shorter. And that is the equation of a rope. That's what that little c is all about. And incidentally, the little c was first put in there by Maxwell in one of his books, but for the value of 300,000 kilometers per second, right? But nobody picked up on that. And there were other writers all the way through the 19th century, the beginning of the 20th century, right? And it wasn't until Einstein in about, I think, 2007 wrote a paper, and he used little c, and after that, other people began to use a little c, and that's why we use the c today as a symbol for the speed of light, okay? Anyways, there you have it. The more you torque a rope, the shorter the links, the more links you have. That's frequency times wavelength. That's the equation of a rope. And so that's one of the things that you can say is evidence. We don't like to introduce evidence because we're not trying to convince you. We're just saying we have a right to use the rope as a mediator for light, okay? At least for light. We'll show that it's also for gravity. Okay, so that's the first issue. The other thing that rope can explain is based on the construction of what we're going to propose here, which is how the atom is constructed, okay, the H atom, okay, and give me a second here. Fill on the other side. 1 second, here we go. And here you see the construction of the atom. Give you a second here. It'll start here in a second. Your two threads that make up the rope, they also construct the atom. One thread goes through the center and constructs the proton star, dandelion as we call it. And then the other one rolls around and forms the electron shell. But you can see it's all made out of the same thread. Okay, it's one thread really in the universe. And they both construct not only the rope, but the atoms. And the ropes connect. That's why the ropes interconnect every atom in the universe. So as you can see, our site is a little different than all the others. We like to think that, or everybody likes to think that they've got something different. No, I think we do have something different here that you haven't heard anywhere else in the world, in any other site, okay? And so, we're proposing a new model for the universe. We think that these people who've been doing research and theoreticians and so on, they misconceive the universe completely. They don't have the slightest idea what this universe is or how it works. Here we have a different version, and I think it works a lot better. That's my opinion, right? But you have to reach your own conclusion. Okay, so what I was saying is that if the atom is constructed by the same threads, twine threads, as the ropes that interconnect them, then we can see why you don't add the velocity or the speed of the train to the light coming out of the train. You have your car, your headlights, and you turn the lights on. Well, if you threw a ball from your car while it's running, you would have to add the speed of the car to the speed of the ball. That's not the case with light. Light has a different speed or a constant speed irrespective of the movement of the source. And there you can see why. If the atom is made of the same material, the same threads that make up the rope, you can see how the atom can slide along there because the threads are going over and through, right? You have the blue one going right through the center the atom, which is what makes up the proton, and the other one goes around and forms out the electron shell. So an atom does not, well, it's torquing, well, it's vibrating and torquing the rope, sending light along the rope. It doesn't have to, you don't have to add the speed of the atom to the speed of light, because the atom is eating into the rope. Okay, so we're explaining two things: the constancy of the velocity of light, the speed of light, and also why you don't add the speed of light to the moving object. Okay, the speed of light is independent of the moving object because the atom does not push light forward. That's another reason why you can't go faster than light, because you're trying to go faster than the threads that make up the atom. So, it answers all those questions. At least we have an answer for them. And again, it's up to people to ponder what I'm saying and reach their own conclusions. Everybody has his own brain, hopefully, and you don't allow yourselves to be influenced by anyone else. You reach your own conclusions. All we can do here is present the theory. Okay, so that's the light part of it. Now let's look at the gravity part of it, see if we can make some sense of it. For this, I usually use this gentleman, because people say, Bill, who are you? We don't know who you are. I've been 29 years at this, but nobody knows me. I'm a great unknown out there, and okay, that's life. But here's a fellow. His name is Richard Muller, and he's a professor. I think he still is a professor at Berkeley University. And he says it just like it has to be said, and you got to listen to him, because he's going to tell you what the specifications for gravity have to be. Anyone who's got a theory of gravity has to exceed if possible, but meet at least what Richard Muller has to say. So listen to him. Don't listen to me. I'm a nobody. Listen to him. He's a somebody. So here, listen carefully. Here goes.
If you have the Earth with its big mass here, and you have you with your little mass here, that every atom on the Earth is pulling on every atom of you. You're also pulling on it. You're pulling on atoms right now on the other side of the Earth. On the other hand, there are a lot of atoms here you're pulling on. You're pulling on all of them. The amazing thing about gravity is it goes right through things.
Okay, so what are the two things that Richard Muller said? Well, it says that one thing is that every atom on Earth is pulling on every atom of you. Every atom of you, is also pulling on every atom of Earth. Now, how do you pull if you don't have a mediator? Again, we need to do physics with physical objects. Mother Nature does not do physics with witchcraft and black magic, or what they call in mathematical physics and theoretical physics, they call it action at a distance. No such monster in our universe. Okay, Mother Nature does not work by black magic. Okay, so it's not action at a distance, not remote control. No, there has to be a physical object, and Muller just told you every atom pulls on every other atom. So there's got to be something between any two atoms, and we're saying it's this rope that interconnects any two atoms. Okay, so here it is again. This is his summary. Okay, just listen to him. Okay, he says, every atom in the Earth is pulling on every atom of you. Okay, I think it's straightforward. You're also pulling on it. Now, what part did you not understand? There's got to be a physical object there. Okay, otherwise, you're doing black magic. You're saying this atom pulls on that one, but there's nothing in between them. Okay, and that's irrational. Okay, and then he says the amazing thing about gravity is it goes right through things. So if you have an object in front of another object in front of another object, gravity goes right through them. You cannot put a shield in front of you to protect yourself against gravity. There's no gravity shield. Gravity goes right through your shield, pulls you and the shield, both of them. Okay, so keep that in mind, okay? Those two things are the things that you have to meet if you have a theory of gravity, okay? If you cannot answer those two questions, you do not have a theory of gravity, period. We're done, okay? No, there's no argument on that. Okay, so we say that we use these ropes, right? Electromagnetic ropes, very thin, extremely thin, unimaginably thin ropes connecting any two atoms, and those are the ones that are going to bind any two atoms in the universe. Any two atoms, okay? That means all atoms are physically interconnected. Every atom in your body is right now connected to every atom in my body, and to every atom in my room here. Okay, that's what we're saying. Okay, I just want you to understand that that is what we're saying. Okay, and here we have a little gift there that gives us an idea that of what I'm saying. You're saying that every atom of that astronaut is connected to every atom on Earth. What's happening is as he falls, the ropes, the interconnecting mediators, in this case the electromagnetic ropes, they fan out. And that's the acceleration of gravity. The closer he is, it's a distance-related phenomenon. The closer he gets, the more ropes that fan out. You're talking about gazillions of atoms that form the astronaut there. Okay, so they just fan out, and that's the acceleration of gravity. Very straightforward, kid stuff, kindergarten stuff. Anybody can understand this, even a child. Okay, so physics is for kids. Physics is easy. Math is a separate issue. Math is hard. You got to go to university to learn calculus, like I did. I know I swallowed a lot of calculus, but you don't need calculus to do physics. Physics is with objects. Physics is the language of physics is illustration. If you can't illustrate your theory, you don't have a theory of physics. And you can't illustrate concepts. Okay, you can't illustrate. I mean, people have tried, and they do illustrate things. But then they're illustrating a concept, right? They're putting a heart for love. So the concept is love, and they're represented with a heart. Or they have a dot, and they use it to represent a point. What's a point? A location. So they use a dot for location. They use heart for love, and so on. And then they start moving the heart around, the love around. They say, no, you got to put the heart back in. You got to put the elephant back in. Okay, you got to do it with objects. Okay, so here you have, again, you can see the different, as the astronaut gets closer to the Earth, he has a different weight for each location, okay? So maybe very, very far away from the Earth, he weighs 1 pound with respect to the Earth if we could measure him there. And the closer he gets, you can see his weight increases, okay? And maybe on Earth he weighs 200 pounds, but somewhere far away he weighs 100 pounds, 50 pounds, 25 pounds, and so on. What we're saying here is, keep this in mind, okay? Weight is location specific. Let me repeat that. Weight is location specific. Weight is a static concept, okay? Weight is not a dynamic concept. You don't need to move in order to have weight. You have weight anywhere around the Earth, what is known as a field. You know, you have different values of the field at different locations, at different distances. So you have weight, whether you know it or not, at different locations. I don't need to measure anything for you to have weight, okay? You have weight, whether you like it or not, at any location. It is a static concept. Okay, and you say, well, how can that possibly be? Are you saying that every atom of us, you know, is bound to every atom on Earth? Every atom of the moon is bound to every atom of Earth? Yeah, that's exactly what we're saying. In fact, I'll let another fellow, his name is Brian Greene, and this is what he has to say, okay? Here he goes. You'll just have to read, okay? Here it goes, okay? Yes, we're connected by not one rope, but invisible ropes, and they got rid of that notion. Why? Because they said, well, I can't see, I can't touch any ropes, anything there, so there's nothing there. It's action at a distance. And what they didn't realize, you have to do physics using things. You can't do physics without things, and they're doing it without things. Or worse, they're putting a concept in there, such as field, energy, mass, and they're going to be doing physical interpretations with mathematical concepts. That's where the problem is. No, there is a rope. Not one rope like Brian Greene said there. There are many ropes, gazillions of them. For every atom of the moon, there's a rope connecting it to every atom on Earth. So the Earth swings the moon around like this. Just as simple as that. I think any child can understand what I'm saying here, okay? It's just like that. That's what gravity is. Gravity has to have a mediator, okay? And it's got to be an elongated, very thin mediator that connects any two atoms in the universe. Straightforward. That's what we propose here, okay? And yes, there's a unification also between light and gravity, that they both have these features, and this is how they represent them. It's the inverse square law, okay? The farther away you go, the light becomes dimmer. It's less bright, right? And the farther you go, gravity becomes weaker, okay? So it's like they have, light and gravity seem to have very similar features, okay? And so what do? Well, we say that with the ropes, you can explain that. Here you have them. The closer you are to, in this case, a screen, right, the more the ropes fan out, okay? And not only do you have a brighter screen, but also like when you approach the Earth, the closer you get, the ropes fan out, and now you have more gravity. You have a greater acceleration, okay? But keep in mind, weight, which is what Newton's equation really measures, right? The closer you get, the stronger gravity is, but it's that force, they say. They use it as a force. The equation is a force equation, but there is no force because any location without any force intervening, okay? Any location, like if we took a snapshot of the universe, God's camera took a snapshot, there would be no motion. You would have weight at that location. And you say, but I haven't moved. I haven't pressed down on the scale. You don't need to measure anything. You have weight anywhere around the Earth, okay? Period. Non-debatable, okay? Okay, and so some people say, well, why can't we touch these roads? Why can't, if they're there, right? And people say, not only touch them, because if you can't touch them, it means we pass our hands through them. In fact, I'll prove this to you. This is an experiment that you probably want to do at home, always in the presence of a relativist, right? And here we have, this little straw. Let me get here in the center. And I'm going to drop it, okay? And if you drop it, it always falls downwards. This is what you'll verify, okay? Now, this is the trick, okay? Maybe you can get another person to help you out, okay? What you do, you have this, right? This is a straw, by the way, so it's kind of thin, okay, and very light. And I'm going to let go of it, okay? And it comes down, right? Now, what you can do, and I'm going to do it here now, very dangerous thing is, I'm going to pass my hand, and you can see that all the ropes that are connecting this straw to every atom on Earth, and I'm passing my hand right through it. So you're saying there's nothing there because I can't see and I can't touch anything here. So if we're going to do it like Mr. Muller said, and every atom of the straw is connected to every atom on Earth, and there's got to be a connector, I'm passing my hand right through all those gazillions of connectors. Okay? So we either do black magic and say action at a distance, remote control, witchcraft, whatever you want to call it, or we do physics, saying there is something connecting every atom of this device to every atom on Earth, and I'm passing my hand right through it. Okay, so you can let it drop, and hopefully you could measure the speed, in other words, the acceleration, which should be 9.86 meters per second square, right? that would be the acceleration of whatever object you drop on Earth, barring, air friction. But if you drop an elephant, there's very little friction there, and you drop a stone, they should pretty much fall at the same time. And if you pass your hand while they're falling, okay, so you pass your hand right through there while they're falling, you'll see that your hand does not affect the acceleration. In fact, you can probably do it with an parachutist. The parachute guy goes slowly, and he's falling on Earth because gravity is pulling on him, right? In other words, he's falling and accelerating due to all these ropes fanning out. And you can pass your hand below the parachutist, and he'll fall at the same rate. Your hand will not affect anything, okay? So, yeah, that's the issue. And people say, well, Bill, you're crazy. You're saying that ropes not only are invisible and intangible, but they go right through each other. Yeah, not only the rope, my hand goes right through them as well. And so how can that be? That's irrational. That's unthinkable. And so, there was a series in the 60s I used to watch a lot, and it was known as the Untouchables. Okay? They were untouchable. You couldn't touch them. Okay? And quantum mechanics also has come up with a whole bunch of untouchables, and nobody questions it. See, here's some examples. Let me read them out to you here. Space.com, around 65 billion neutrinos manage to stream through every square inch of your body every single second with no discernible effect. They go right through you, through every atom, through every thing that builds your body. Wikipedia, neutrinos typically pass through normal matter unimpeded, undetected. And nobody questions this? I mean, when I say the rope goes right through the rope, you say, no, Bill, you're crazy. How can a rope go through a rope? But here, the neutrinos go through everything, untouched. They go right through things, and nobody questions that. Nobody says, hey, how can that possibly be? How can neutrinos go through things and not touch them? You have a little ball going through another ball, right? And they go right through it. Nobody questions that. Photons cannot couple directly to each other in a fermionic field, according to the Landau-Yang theorem. So photons also go through things. How about the gravitons? They exist then like photons, and unlike gluon, gravitons do not interact with other particles of their kind. They always say they're weakly interacting particles. They interact weakly with matter. They use that fancy wording. What they're saying is it goes right through it. That's what they're saying. And so you say, well, how can that possibly be? And nobody questions that. See, this is the problem. The problem is that everybody questions when I use the rope. And they say, well, how come nobody questions the particles that these people talk about? Now, there's a caveat there. A tiny caveat you have to keep in mind, okay? Particles can only push. Okay? Particles go one way, okay? A rope or anything that's pulling, right, goes in two directions, okay? And so when people say, well, hold it, you're saying you're pulling and something cuts right across it and doesn't cut it? And so that's where people start asking the question. But really, it's no different with particles. If you take two hoses full of water and, just let the water run on both hoses, you put them one against the other, the water will bounce. So if particles go through each other, not a single one should bounce out. So in that sense, there's no difference between push and pull. But people start questioning the pull because they say, hold it, it cuts across the rope, but it doesn't cut in and continues pulling. Yeah, it's like a river going through another river. It doesn't maybe stop the other river from flowing. Think of it like that. But yeah, that's Mother Nature's universe. So two lessons you got to draw from what we've never made assumptions before is, one, that you need objects to do physics, and the other one is that the objects Mother Nature uses can cut across each other. Not only are they invisible, intangible for our regular everyday macro world, they go right through each other. And until you come to terms with that, until you realize that, you're never going to understand what is out there in our universe or how it works. So those are two things you need to understand. You need physical objects to do physics. You can't do physics with concepts, okay? And the objects Mother Nature uses, the ones she uses as mediators, they go right through each other. Until you come to terms with that, you realize that, you won't understand how this universe works. And here what you have, here's an example of another thing that goes right through each other and nobody questions it at all. Here you have Arvin Ash, talks a lot about, has a show on physics, right? And what he does, he talks about fields. I want you to listen to him because he's telling you all the fields that we have out there. Now listen carefully to what he has to say, all the fields that are out there. Okay, here it goes. Listen.
All these fields extend out in all of space-time. In other words, the fields are always there and exist everywhere, including inside your body. Now, although they exist everywhere and you can't see them, they are not nothing. They are teeming with virtual particles. These are particle-antiparticle pairs that get created and destroyed. They come in and out of existence constantly. These virtual particles can't be measured, but nature allows the creation of these virtual particles by letting them borrow energy from the vacuum.
Okay? So what is he saying? He's saying there's all these fields. The vibration of these fields creates these particles, right? They're not discrete particles, they're peninsulas, not islands, because they stick out of the field, okay? Great, let's not worry about that. But there are many fields. There's a field for every particle out there, and they stretch forever. Well, don't these fields that make up particles, right? Don't they go through each other? Nobody asks that question. We have all these fields that are going through each other. We have all these waves coming out of two black holes that are merging. All these waves travel where? Along space-time, hopefully, right? And we have all these waves from all the black holes in the universe, and they don't collide, they don't interfere with each other. How can you measure anything out there if you have gazillions of black holes, not to mention other galactic components sending waves everywhere? The universe should be a mess. And they claim that they measured waves coming from the collision of two black holes. There's something wrong with that right there and then, okay? But yeah, so here we have, again, a synthesis of what good old Arvin Ash said. All these fields extend out in all of space-time. The fields are always there and exist everywhere. Fields, right? So they're all superimposed fields. They create these particles, right? And he's saying they're not nothing, they're something, okay? Something means that, you have a ball or whatever a particle is, and all these vibrating fields, they're superimposed, I guess. Well, how can they go through each other? Why doesn't anybody question the fact that all these fields, energies, waves, what else? They don't go through each other. Nobody questions this, neutrinos, and so on. So this is the issue. The issue is, before you come and say, look, you're crazy, Bill. How can ropes go through ropes? Well, first go to quantum and ask them, how do balls go through balls? And that's what you got to ask them. Okay? And until you get that question answered by them, don't question the rope. Okay? Otherwise, we all have to accept what quantum has already accepted. Things go through things. In Mother Nature's world, invisible, intangible world, we just have to come to terms with that. Nobody has been able to come to terms with that in the last 10,000 years. And I'm asking you, if you're going to understand this universe, what is out there, what exists out there, right? Physics is the science of existence. Physics has to tell you what exists out there. A physicist has to tell you. The assumption you have to make is, first, there are objects that you cannot see or touch, and these objects do go through each other.